problem number 20 reads like this. It says 20 feet of wire is to be used to form two figures. In each of the following cases, how much wire should be used for each figure so that the total enclosed area is a maximum? Now, in the first part here, part A, we want to find the area or the way to maximize the area for these two figures, a square and an equilateral triangle. So we've got 20 feet of rope, called X and Y, or 20 feet of, what did they say? Wire. Yeah, 20 feet of wire. So I know that X plus Y equals 20. Kind of keep that in mind. And I need to cut it and then bend it into these different shapes. My ultimate goal is to maximize the areas here. So let's list the areas. So we'll start with the area of a square, or the area, yeah. So area of the two figures would be the area of the square plus the area of the triangle. And let me note that it's an equilateral triangle. And here's something that I'd probably give you on an exam. The area of an equilateral triangle has a special formula. It's not something that I expect you to know. It's, let's see, its area, let's see. So if I have an equilateral triangle of side S, then the area is square root of 3 over 4 times the length of the side squared. So that's just a little tidbit. I really don't expect you to know that. It's something you can prove pretty easily with trigonometry, maybe even geometry. I remember I derived it with trig. So let's think here. Area of the square, that's going to be the side squared. And then this one is going to be square root of 3 over 4 s squared. But I can't really use s for both of these. That's just kind of a stand-in right now until I get something better. Suppose we cut this at a length x and use x to make up our, let's see. Let's do the triangle with, I guess the way it's written, we'll do it with the rectangle. So if I use x to make the perimeter of my square, what's the length of each side then? If x is the whole, whole perimeter, what's the length of each side? 1/4 x. So this would be 1/4 x. This is going to be y over 3. So that's the length of the side for the triangle. So, all right, let's make a little bit of progress here. 1/4 x squared plus square root of 3 over 4. Well, it's not going to help me out to have a y here, because then I'll still have something that depends on two variables. So let's take note of the fact that y equals 20 minus x. That just comes from the fact that we have 20 feet of wire. So instead of s, the length of the side, I can put 20 minus x over 3 for the length of the side. So 20 minus x over 3. And that whole thing is going to be squared. Well, that's kind of what I needed here, is that I wanted some function of one variable that talked about the overall size of these shapes, that is the area of these shapes. And I've got it. Let's clean this up a little bit in order that we can differentiate this. So let's see. If I square this out, I'll get 1/16 x squared plus square root of 3 over 4. Well, it's going to be 4 times 9, so it'll be 36 times 20 minus x squared. Picture, function, interval. 36. Thank you. Interval. What could the values of x range between? Good. 0 and 20. Has to be somewhere between these because that's all you've got in terms of the amount of wire. So the interval would be 0 to 20. Actually, we could probably include the endpoints here, because if you include the endpoints, basically you're saying, all right, I'm going to put all the material in the square or all the material in the triangle, one or the other. Let's see what actually maximizes this. So for A prime, 2 times that's going to give me a 1/8 x plus, bring the 2 out in front, 2 square roots of 3, that'll cancel into the 36. 20 minus x to the first power times what? Times -1. Good. Got to apply the chain rule there. So derivative of the outside times derivative of the inside. So overall, 1/8 x minus 18, or excuse me, square root of 3 over 18 times 20 minus x. Now it's just a matter of solving for x, set it equal to 0. I think probably what I'll do is I'll distribute this term to both of these. So 1/8 x minus, let's see, we're going to do some cancellation. There's going to be a 2 that'll cancel, so I'll have 10 square roots of 3 over 9 plus square root of 3 over 18 times x. Yeah, it's looking kind of ugly, isn't it? Equals 0. That's okay. The thing that caught my attention for a second, I looked at this and thought, oh my gosh, we're going to get a negative value for x. That would be a disaster, right? You can't have a negative amount of wire. So let me move this term to the right-hand side. So I'll get 1/8 plus square root of 3 over 18 times x. So factoring the x out of those two equals 10 square roots of 3 over 9. If we divide both sides by this number here, 1/8 plus square root of 3 over 18. Ooh, that's a really mighty ugly looking number there, isn't it? You could probably clean it up. This isn't an algebra class. I'm not going to really fuss about it. Let's see if we can get a numerical value. If you were bent on cleaning it up, I'd probably multiply everything through by, say, 72. 72 over 72. Because 72 is the lowest common denominator of these secondary fractions. So it would cancel them out. It would clean things up pretty nicely. But let's just see if we can get a decimal value for this. With something ugly like this, you might want to break it up into 2 little parts. So here's how I'll do that. It's just kind of an idea here for you. Let's calculate the numerator first. 10 square roots of 3, x at the root, divided by 9. You know what? I'm going to store that in x. So I've got that part stored. Now for the denominator, it's 1/8 plus square root of 3 divided by 18. That's my denominator. I need to take x divided by that. So x divided by my previous answer, second opposite key, gives me something like that. So about 8.7 would be the right number there. So 8.7 units for the square, and then the rest for the rectangle. So you can do 20 minus answer for the amount of wire that you would use for the rectangle or the triangle. Any follow-up or thoughts on that one? Let's do one last one from the handout. That's problem number 16. So I'm just going to look at this and describe it based on the diagram. You've got a point here at 12 and 0, and this function is y equals the square root of x minus 8. Our goal is to try and find the point here on this curve that's closest to this one here, that minimizes this distance. So there's your picture. And it's this distance that I want to try and minimize. I want to make that as small as possible by choosing a point on this curve that is as close as I can get to 12 and 0. It was funny, a couple years ago, they used to have this problem, the same problem, except they had the point over here. And they said, well, we'll choose a point on this curve that minimizes this distance. And it was like, well, done, right? You don't have to use calculus for that one. It's kind of silly. So, all right, they've wised up in the more modern edition here, and they put it over inside of this half of a parabola. One thing that I should probably remind you of is the distance formula, the distance between 2 points. So let's do that up here. If you have, say, x1 and y1 and x2, y2, what's the formula that allows you to calculate the distance between those 2 points? Square root of x2 minus x1 squared plus y2 minus y1 again squared. So if you're a little rusty on that formula, there it is. So picture function, well, this kind of depends on 2 points right now. I mean, here's one of our points, x1, y1. I'll give this a generic x and y as our second point. So our distance formula is going to be this. I am going to play a little trick with that in a little bit. So at the moment, distance is going to be the square root of, let's see, we'll do x minus 12 squared plus y minus 0 squared. There's a couple problems that we're going to run into here. But we can make our life easier. We want to minimize this distance. And here's a trick that I remember when I saw this in a calculus class and bothered me a lot. I'm not sure if it's just that I've seen this problem often enough that I've gotten around it, but minimizing this distance, you know, you can do that and it will work fine. But because of the root here involved, it's kind of a pain. Minimizing the distance is also going to be the same, give us the same point as minimizing the square of the distance. So if I square both sides, then this problem becomes a little bit easier because I get rid of the square root. Minimizing the distance over the square of the distance is going to lead to the same conclusion. Now, there is one more thing that I want to work on. Right now, this depends on two variables. I'd like it to depend on one variable. Any bright ideas out there? Yeah. Good. Thank you both. We have y, right? Y equals the square root of 8 minus x. So this is x minus 12 squared plus square root of x minus 8 squared. If I square this all out, I'll get x squared minus, that'd be what, 24x plus 144 plus x minus 8. If I combine like terms, then I'll get x squared minus 23x plus 36? 144 minus 8? Okay. All right, so I thought I was wrong, but I was merely mistaken. Okay. What do you want to call that function? I don't want to use d because I already used d a little bit. Let's just call it f of x is x squared minus 23x plus 136. And that, despite the way it might look, looks like a 28 or something like that. It's actually minus 23. My bad. (23x). So do I want to maximize this function or do I want to minimize this function? Minimize this function. What interval works for this function? Are there any natural restrictions for x? Yeah, x has to be at least 8, right? Otherwise, you're not talking about a point in the curve. 8 to what? 8 to infinity, although it's probably very unlikely it's going to be a point way out here at infinity. Oops. So, yeah, x has to be somewhere in the interval of 8 to infinity. So let's try and minimize that one then. F of x was x squared minus 23x plus 136. F prime of x is going to be 2x minus 23. Set that equals 0. I get 2x equals 23, or x equals 11.5. Okay. Does that look reasonable? Does that sound reasonable? Yeah, that looks pretty good. Okay. So at least passes kind of a cursory glance at it. It looks pretty good. Now, one thing that you can do for yourself, and really it was a question on the test, how do I know that that point is actually a minimum point? Well, we could do the first derivative test, x, f prime, 11.5, etc. But how about this? Let's take a look at f double prime of x. What's the second derivative? Don't think too hard. So there's the first derivative. What's the second derivative? 2, right? And no matter what, this is always greater than 0, right? For any value of x. What's that telling you about the concavity of this function? concave up. So if you have a critical point in a concave shape, what does that critical point have to be? A minimum or a maximum? Minimum. Done, right? We don't have to, I mean, you could play around with, you know, it's decreasing here, it's increasing here. Okay, you can play around with the first derivative test and get that same conclusion. That's fine. But this is pretty quick. I mean, it's concave up. It's a critical point. It has to be a minimum. So x equals 11.5. I think that's our, yeah, that's it for this one. We can't solve for y. Let's solve for y. That'd be the square root of 11. So y would be the square root of 11.5 minus 8, or the square root of 3.5. Square root of, call it 7/2. You probably get this answer in the back of your book. Square root of 14 over 2. They'd probably rationalize that, which would be annoying, but I'd be happy with this one, or this one.